Warm welcome to one and all present here. Today, Sarthak Garg of batch EB17 having enrollment number E20CSE375 has got the golden opportunity to present on the topic case study of HPC product solution on any big company. So here we would be discussing about the case study of high performance computing on big companies like Google and Azure. So introduction. High-speed computing, originally implemented only in supercomputers for scientific research. Tools and systems available to implement and create high-performance computing systems. Used for scientific research and computational science. Main area of discipline is developing parallel processing algorithms and software so that program can be divided into small independent parts and can be executed simultaneously by separate processors. HPC systems have shifted from supercomputer to computing clusters. So what is a cluster? Cluster is a group of machines interconnected in a way that they work together as a single system. What is its terminology? The things which are used. First, node, individual machine in a cluster. Second, head, master node, connected to both the private network of the cluster and a public network, and are used to access a given cluster. Responsible for providing user an environment to work and distributing tasks among other nodes. Third, not the last one, compute nodes, connected to only the private network of the cluster and are generally used for running jobs assigned to them by the head node. There are some more terms about the cluster, types of clusters. Storage. Storage clusters provide a consistent file system image, allowing simultaneous read and write to a single shared file system. High availability. Provide continuous availability of services by eliminating single points of failure. Load balancing. Sends network service requests to multiple cluster nodes to balance the requested load among the cluster nodes. High performance. Use cluster nodes to perform concurrent calculations. Allows applications to work in parallel to enhance the performance of the applications. Also referred to as computational clusters or grid computing. Benefits of clustering: reduced cost. The price of off-the-shelf consumer desktops has plummeted in recent years, and this drop in price has corresponded with a vast increase in their processing power and performance. The average desktop PC today is many times more powerful than the mainframe computers. Processing power. The parallel processing power of a high performance cluster can, in many cases, prove more cost effective than a mainframe with similar power. This reduced price per unit of power enables enterprises to get a generate ROI. ROI is return of investment. Scalability. Perhaps the greatest advantage of computer clusters is the scalability they offer. While mainframe computers have a fixed processing capacity, computer clusters can be easily expanded as requirements change by adding additional nodes to the network. Some more benefits. Improved network technology. In clusters, computers are typically connected via a single virtual local area network, virtual LAN, and the network treats each computer as a separate node. Information can be passed throughout these networks with very little lag, ensuring that the data doesn't bottleneck between nodes. Availability. When a mainframe computer fails, the entire system fails. However, if a node in a computer cluster fails, its operations can be simply transferred to another node within the cluster, ensuring that there is no interruption in a service. Invention of HPC. Why do we need? Why was HPC invented? Need for ever increasing performance and visionary concept of parallel computing. Why we need ever increasing performance? Computational power is increasing, but so are our computational problems and needs. Some examples. Case 1. Complete a time consuming operation in less time. First, I am an automotive engineer. I need to design a new car that consumes less gasoline. I would rather have the design completed in 6 months than in 2 years. I want to test my design using computation simulations rather than building very expensive prototypes and crashing them. Case 2. Complete an operation under a tight deadline. I work for a weather prediction agency. I'm getting input from weather station sensors. I would like to predict tomorrow's forecast today. Case 3. Perform a high number of operations per second. I'm an engineer at Amazon.com. My web server gets 1000 hits per second. I would like my web server and databases to handle 1000 transactions per second so that customers do not require experience bad delays. Some examples. Where are we using HPC right now? Used to solve complex modeling problems in a spectrum of disciplines. Topics include artificial intelligence, climate modeling, automotive engineering, cryptographic analysis, geophysics, molecular biology, molecular dynamics, nuclear physics, physical oceanology, plasma physics, quantum chemistry, solid state physics, and structural dynamics. HPC is currently used applied to businesses uses as well. Data warehouses, transaction processes. These are the list of some top 10 supercomputers for HPC as per June 2020. This is the world's fastest supercomputer developed by China. Its name is Tianhan 2, Milky Way 2, and it's in China's National University of Defense Technology. Changing times from 1986 to 2002, microprocessors were speeding like a rocket, increasing in performance an average of 50% per year. Since then, it's dropped to about 20% increase per year. What was the problem? Up to now, performance increases have been attributed to increasing density of transistors. But they are inherent problems. A little physics lesson. Smaller transistors equal to faster processors. Faster processors equal to increased power consumption. Increased power consumption equal to increased heat, and increased heat would equal to unreliable processors. An intelligent solution. Move away from single core systems to multi-core processors. Core. So core is a processing unit. Introduction of parallelism. Welcome to parallelism. But adding more processors doesn't help much if programmers aren't aware of them or don't know how to use them. Serial programs don't benefit from this approach in most cases. Parallel computing, form of computation in which many calculations are carried out simultaneously, operating on the principle that large problems can often be divided into smaller ones, which are then solved concurrently, that is, in parallel. So we need to rewrite serial programs so that they are parallel. Write translation programs that automatically convert serial programs into parallel programs. This is very difficult too. Success has been limited. Parallel computing example, a simple example, compute n values and add them together. So this is a simple logic of adding n values and doing it in a parallel execution. Now example is we have p cores, p much smaller than n. Each core performs a partial sum of approximately n by p values. So this is an example of parallel computing. More example, okay, parallel computing. Some coding constructs can be recognized by an automatic program generator and converted to a parallel construct. However, it's likely that the result will be a very inefficient program. Sometimes the best parallel solution is to step back and devise an entirely new algorithm. Parallel computer programs are more difficult to write than sequential programs. Potential problems, race conditions, output depending on sequence or timing of other events, communication and synchronization between the different subtasks. Parallel computing classification. Semiconductor industry has settled on two main trajectories. Multi-core trajectory CPU. Cores, heavyweight threads, better performance per thread, maximize the speed of sequential program. Many core trajectories. It is GPU. large number of much smaller cores to improve the execution throughout of parallel applications. Fine line with threads, single thread performance. CPU versus GPU, okay, this we already know somewhat. Why GPU? GPU is a massively parallel architecture. Many problems map well to GPU style computing. GPUs have large amount of arithmetic capability, increasing amount of programmability in the pipeline. CPU has dual and quad core chips, but GPU has currently 240 cores, GeForce GTX 280. Memory bandwidth CPU 3.2 GB per second, GPU 141.7 GB per second, which is very much high. Speed CPU 20 G flops per core, GPU 933 single precision or int 17 double precision G flops. Direct access to compute units in new CPU plus GPU. CPU and GPU is a powerful combination. CPUs consist of a few cores optimized for serial processing. GPUs consist of thousands of smaller, more efficient cores designed for parallel performance. Serial portions of the code run on the CPU. Parallel portions run on the GPU, performing significantly faster. This idea ignited by the movement of GP-GPU, general purpose computation of GPU. Using a GPU, graphical graphics processing unit, together with a CPU to accelerate general purpose scientific and engineering applications. GP-GPU computing offers speed by offloading compute intensive portions of the application to the GPU, while the remainder of the code still runs on the CPU. Data parallel algorithms take advantage of GPU attributes. Large data arrays streaming the output. Fine-grained SIMD, single instruction multiple data parallelism. Low latency floating point computation. HPC parallel computing models associated with different computing technology. Parallel computing in CPU clusters, general purpose GPU program. Operational model CPU originally was designed for distributed memory architectures. Tasks are divided among P processes. Data parallelism, compute intensive functions should be selected to be assigned to these processes. Functions that are executed many times but independently on different data are prime candidates. That is body of for loop. Execution model allows each task to operate indirectly. Memory model assumes that memory is private to each task. Move data point to point between processes. Perform some collective computations and at the end gather results from different processes. Need synchronization after the end of tasks of each process. Programming language MPI. Message passing interface. An application programming interface API specification that allows processes to communicate with one another by sending and receiving messages. Now, a de facto standard for parallel programs running on distributed memory systems in computer clusters and supercomputers. A message passing API with language independent protocol and semantic specifications. Support both point to point and collective communications. Communications are defined by the APIs. Goals are standardization, high performance, scalability, and portability. Consists of a specific set of routines, that is APIs, directly callable from C, C++, Fortran, and any language able to interface with such libraries. Program consists of autonomous processes. These processes may run either the same code or different codes. Processes communicate with each other via calls to MPI functions. Operation model GPU. Both CPU and GPU operates with separate memory pools. CPUs are masters and GPUs are workers. CPUs launch computations onto the GPUs. CPUs can be used for other computations as well. GPUs will have limited computation communication back to CPUs. CPU must initiate data transfer to the GPU memory. Synchronize data transfer. CPU waits for transfer to complete. Asynchronous data transfer. CPU continues with other work. Checks if transfer is. GPU cannot directly access main memory. CPU cannot directly access GPU memory. Need to explicitly copy data. GPU is viewed as a compute device operating as a coprocessor to the main CPU host. Data parallel. Compute intensive functions should be offloaded to the device. Functions that are executed many times but independently on different data are prime candidates. That is body of for loops. A function compiled for the device is called a kernel. The kernel is executed on the device as many different threads. Both host CPU and device GPU manage their own memory, host memory and device memory. Programming language CUDA. Welcome to CUDA. Compute Unified Device Architecture. Introduced by NVIDIA in late 2006, it is a compiler and toolkit for programming NVIDIA GPUs. API extends the C programming language, adds library functions to access GPU, adds directives to translate C into instructions that run on the host CPU or the GPU when needed, allows each multi-threading parallel execution on all thread processors on the GPU, runs on thousands of threads. It is scalable memory model. General purpose programming model. User kicks off batches of threads on the GPU, specific language and toolkit. Driver for loading computation programs into GPU. Standalone driver, optimized for computing. Interface designed for computer. Graphics free API. Explicit GPU memory management. Objectives. Express parallelism. Give a high level abstraction from. Thank you.